Let's start. All right, so we were examining this system here where we have a reservoir and we look at a small part of it that I'm calling this microstate, and I think of it as just a small part of the reservoir. I think of it as two things. I developed it as sort of two things next to each other, and then I said, let's make one really small. And in fact, the concept I want is not exactly even that. It's more like if I have one overall system, a bath of water, I'm going to take just a tiny little bit of it that's much smaller than the main part, and I'm going to consider it to be a state, a system I'm going to look at. And the rest of it is so big, I call it a reservoir, a heat reservoir, if you will. Okay? And energy can be exchanged back and forth, just in the way we've been discussing. And then I wrote the probability that we have that state, that system in the state S. So that's a label for the state of this microstate. Someone asked after class last time, what do you mean by state? In this sort of analysis, all the particles have some energy. To say they're in a particular state is just to say each particle has a specific energy. Right? That's all I really mean. For the particle in a box, quantum functions, a state would be that, there was a particle in n equals whatever. It's just listing the energies of the particles, specifying their quantum numbers, which will typically specify their energies. Okay? So this is just simple, the notion of probability. I ought to be able to count the total number of states of the system for this particular combination of ES and ER, and then I'll divide by, in principle, summing over all possible states and counting up the number of ways that the system can arrange itself. Note that it's a little bit of a funny notation, and I don't want to confuse you. I wrote that it's the number of degrees of freedom, the number of states available when I have energy ES and energy ER. Those two are not independent. I really could have just written ES or ER. I write it out explicitly, but they're just related because the total energy is, the fixed thing. And let's not actually go try to think about calculating the denominator. Let's just say that's equal to some constant times W total of ES and ER. Okay? That's the probability that this system is in a state S. This C prime is just 1 over, it's this thing, it's 1 over this, okay? It's just some constant that in principle I got by analyzing that. Okay? Now, W total is W of the reservoir times W of the little microstate. Okay? But I chose, I'm not sure you remember this, but I chose S in a single state. Just for the purposes of constructing this derivation, I did that. That's just to say WS is 1. Okay? So I've put the microstate in one system, and therefore PS is C prime times WR. That's all it is. Because the microstate's in one state. There's only one thing to count there. I'll continue to write that, well, it depends on the energy in R, which depends on the energy, which is related to the energy of S in a simple way. In fact, in particular in this way. I wasn't writing tote, I was writing T. Okay? Just a simple idea. Okay? So now what I'm going after, remember how this started. I followed the example in the book where we actually said, well, if I have these quantum oscillators and the total energy is given by some capital M, what's the number of states there are if I take one particle and look at it at some energy? So I'm seeking a probability that this system will have a state S with some associated energy. And so I've gotten to this point that probability is a constant times I have to count how many states there are in the reservoir depending on what this energy S was. And the way I've constructed it, I'll write it over here, I made ES much, much less than ER and E total. So this screams out for a Taylor expansion, right? I should do a Taylor expansion, at least in principle, I should do a Taylor expansion and then see where that gets. This is a small term compared to a big term. Now, it turns out, and this I'm not going to justify in any rigorous way, that in fact you can't even do a Taylor expansion yet. Remember how W, for these, Avogadro's number of particles, I explained that if I look at W versus energy, the number of states available to the system, even without calculating anything explicit, although there is the explicit calculation for quantum oscillator in the book. Sorry, it doesn't look like that. It just goes nuts. It's a completely incredibly steep function where typically the types of numbers you're getting are 10 to the 10 to the 23rd. Okay? So I don't want to do that. I don't want to just take a Taylor expansion. The right thing to do is to do a Taylor expansion. Taylor expand the logarithm of WR of ET minus ES. Okay? Around ER equals ET, which is to say ES equals 0. Okay? So I'll write because this is just ER. So I'll write that the natural log of W of ER is approximately equal, well actually it's exactly equal to W at ET. That is W at ER equals ET plus D natural log dW. And this is W of system of the reservoir, dE of the reservoir, evaluated when E reservoir equals ET times times ER minus the expansion point. I'm expanding in variable ER around ET plus 1/2 blah, 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 higher order terms, which I'll throw out. And so the statement I won't prove is that if I do this, and there's a logarithm here. If I take the logarithm and then do a Taylor expansion of the logarithm, that's a slow enough function that this term will be big, this term will be small, higher order terms in ER minus ET, which is, by the way, just ES. So that's ES squared, then there's a cube. Those will be negligible, right? If I hadn't done the logarithm first, I couldn't throw out these higher order terms. And you'll just have to accept that. So if I erase that, because those are negligible, and I throw them out and put a twiddle there, that's the statement. Now look at this beast here. The change in the natural logarithm of the number of states divided by energy, that is just, remember, 1 over temperature. There's a K in there. That's 1 over KT of the reservoir. Okay? I define temperature that way. I mean, the reason I define, this all comes together. The reason I define temperature that way is because it's this sort of term that matters. How the number of states is changing with energy. Okay? And this was just ER minus ET, which is actually, I'm sorry, it's minus ES, right? ET is bigger than ER. Okay? So I just wrote that the natural log of W of ER is approximately equal, and I'll just throw away the approximate. We just have to remember that it was approximate. But in fact, we're going to say that it's, we're just going to forget that it's only approximate. It's just 1 over KT. That's it. Okay? And if that's, but done for, this is inside of a logarithm. So I want to exponentiate each side. All right? So just take the exponential of both sides. So e to the natural log of WR of ER equals e to the natural log of WR of the total energy times exponential of minus ES over KTR. And of course, that is just, the exponential of the log is just the thing again. All right. This is the number of states available to the system with a fixed total energy T. That's just a constant, okay? Which we'll call C. Well, that's just a constant. And we had that P of S, the probability of state S, was C prime, or we're just writing it here, it was C prime times WR of the energy at R. So finally, using the value from over there, calling this constant times C prime, just some new constant C, I have that result. I've dropped the R from the temperature because at this point, I had this system where there was this big reservoir, often called a heat bath. And I simply meant it was the big system, and I'm looking at a little subpart of it. And the temperature is this concept that makes sense to talk about for the big system that of which I'm looking at a little part and examining it. So strictly, I did derive this only for the reservoir, but I just dropped the subscript by convention and just call it T. And this is the fundamental result. This is called the Boltzmann distribution. Okay, so you guys are quiet. Is this okay? I mean, it's mathematical, okay? But it's not too bad. All I did was carefully write down what elements, all I did is I went through this carefully. I wanted to use the one little bit of mathematics that I better take the logarithm before I did a Taylor expansion. That's all I've done. And you remember that the curve that I sort of wrote the numbers down, the formula for down last time, that's in the book that I didn't do, the quantum harmonic oscillator. I just wrote the formula that gave us this curve. The curve looked like an exponential. The curve looked like a probability versus energy that did that. Well, by God, this is the more general result, and it really is an exponential. Now, this was an approximation because I did a Taylor expansion and threw out higher order terms. And in fact, if you go in the book, they basically followed the same thing we did. The book skips this derivation of the Boltzmann distribution for reasons I can't fathom, because I find this it's a little bit abstract, but it's not much algebra. And this is the derivation like that's in an advanced textbook. It's just this argument. Anyway, there's another derivation they've got in an appendix if you're interested. A slightly less general derivation. Anyway, the book compares this curve to the carefully calculated exact curve for that quantum harmonic oscillator. And they're very, very close. And the only reason they weren't exactly dead on is because we took the number of particles to be 10. If the number of particles is large, then these approximations here are absolutely, completely fine and exact. And I can remove my little tilde. And this is completely valid. This only breaks down when the total number of particles in the system is few, tens, hundreds. Any real macroscopic system, that's an exact for all intents and purposes. So this is a beautiful result. Okay? The way I think of it is not, again, I kind of said this before, but let me just repeat. I draw this diagram of these two systems, but I really want to think of this as just being a part. Let me just change the picture a little bit. It's really just, I'm going to look at some part of that system, okay? And in fact, what I really am going to do is I'm going to look at a single particle in that system. And that makes more sense. Okay? I'm going to look at a single particle and ask about that particle having the energy E. This is simply the probability, and let me change my notation even just a tad, just to be a little more explicit. I'm really asking about the probability that there's a particle having an energy E sub s, because it's in a state S. It's just that. And there was nothing, and of course these notions were general. I didn't say anything about which particle I'm looking at. And if all the particles in here are the same, it's a gas, it's a liquid, it's a solid, then this is going to apply globally. I don't have to talk about which little special piece I looked at. And this is really, it's profound. There's this very simple idea that I have the exponential of the energy divided by kT, and that's the probability that any one particle in the system will have that energy. And just to speak one last thing about this result, where did it come from? This mathematics was simply saying, if I give any one particle more or less energy, I'm borrowing the energy from the reservoir. I'm not borrowing, I'm taking it, because the total energy is conserved. And the effect of giving any one particle more energy is to exponentially decrease the total number of states left for the reservoir. And vice versa. If I give the particle less energy, I give the reservoir more states. And then that's the reason that this arises. Okay? But now when we have that, we can calculate a whole bunch of things. This is a huge thing to have gotten that. And I did show you this in the first lecture, and I said, you know, we'll derive it. And indeed we have, okay? Okay, so just a couple of comments on this before I do attack a real system. How will I find C? Okay, we find C you find C as follows. Assuming we're talking about a quantum system where there's discrete states. It's just the normal, we call what we always call the normalization condition, the same sort of thing we did in quantum mechanics to find the normalization of a wave function. I just simply say 1 is the sum on the probability of all states. So in other words, 1 is the sum on all states. Okay? So C comes outside of the sum. Just a very simple thing. Okay? It turns out when we work with this, you know, we went through some hoops to get to this point. And I had to draw these reservoir, and I had to like talk about a microstate was connected to it. And I had to do this fairly abstract reasoning. One of the beautiful things about statistical mechanics is once we've got this though, we kind of forget about all of that. And you're going to very mechanically just say all the time, the probability is proportional to the energy exponent of this thing with a constant out front. You find the constant in a straightforward way. And then we find averages and such in a straightforward way. For instance, what's the average energy in a system? The average energy in a system is it's the probability of some state which has an energy times the energy of that state, sum over all the states. That's all it is. Which is equal to, just to write it out, all I did is the P I plugged in and the C I put in the formula I found, right? So it's just straightforward if I wanted to do something else, right? I just have this probability factor. Notice that there is one slightly subtle issue. The book kind of makes a big deal about this because it is important, but it's very straightforward. It's just simply that you may well have more than one state with the same energy, okay? And so when I'm adding these states up, this isn't exactly the probability of an energy. It's the probability of one state with that energy. If I have some number of states that have the same energy, I should talk about it a little differently. I could talk about the probability of an energy, and that's all right. I just take this thing and I multiply it by the number of states that have that energy. Just a slight normalization change, and that's okay. All right? Any questions or? All right. So let's do Okay, and so in terms of what you're going to be responsible for, actually, I apologize, I haven't assigned the homework. I'm still trying to figure my way through this. I really want to tonight because then you'll have the weekend and it'll be due Friday. And it's actually probably not going to be hugely long. I mean, it's one chapter, okay? Although I thought it was going to be long, but I don't think so now. It'll be sort of normal. What we've done so far is fairly abstract, and I can't really test you that much on it. But now what we're going to start to do is calculate things. Okay, so from here on, we're getting into problems that are a little more practical. The stuff with the combinatorial stuff, that's all practical, and I can give you problems on that. But it's not real. I mean, the applicable part, the important part of statistical mechanics is what we're going to do next. The reason I had to take you through all that stuff with the the binomial distribution and whatnot was to kind of show you the underlying stuff, okay? So, we're going to find, let's examine an ideal gas. All right. So what do we know about a gas? So this is not going to be a quantum mechanical thing. Statistical mechanics is absolutely more not just simply a quantum mechanical thing. I used the language of quantum mechanics quite a bit because it made sense to talk about discrete energy levels. And exactly, 3 particles in one energy level, or a particle with an energy. We don't have to have really done it that way. I could have been sort of using distributions where there can, smooth, continuous function of energy all along. And indeed, this is I'm going to apply it. That's what I'm going to do now. We'll apply it to a classical gas. So what's the energy in a classical gas? It's just the kinetic energy. It's 1/2 mv squared. Okay? So I have the probability of E, and I'm going to drop that S. It's now implied. I'm talking about the probability of any one particle in the gas having an energy E. Okay? Usually when, in fact, we write down the Boltzmann distribution, we drop this S. It's implied. Okay? It's implied that I was talking about a single particle or a single microstate, but usually we think of a single particle. It's going to be some constant times e to the minus mv squared over 2 over kt. Now, the thing is that the most common analysis of a gas is to think about, well, not the energy of the particles, but their velocities. We're going to derive a famous result. And there's a number of reasons for this. I think one reason is because you can measure the velocity of atoms. There are mechanical methods to measure the velocity of atoms in a gas by making them go through a slit system such that only certain velocities get through. And people did these measurements, when people were figuring out all of this, people did these measurements. It's also important for thinking about things like the speed of sound in a gas. Plus which, have you guys seen, has anyone not, have you all seen the Maxwell-Boltzmann, it's called the Maxwell-Boltzmann distribution of velocities in a gas, like in a chemistry book? Who's seen that? So a lot of you have not seen it. Yeah? Okay. Well, that's what we're going to derive. All right? So there's just one little tweak. Going from something where there's discrete energies or discrete states to continuous states involves the notion we had before of kind of a probability density. All right? So I got to talk about that a minute. The first thing is that I'll draw, this is not x, y, and z. This is velocity x, velocity y, and velocity z. I think about a vector, which is the velocity vector. It's got an x component, a y component, and a z component. And I want to think about the probability of having v between v and v plus dv. And what I'm going to do next, I'm actually not going to do very much, and the hardest thing about it is writing down exactly what I mean by definition. Okay? So I have to write all of that. Basically what I'm saying is if I have a little bit of some small increment in Vx and in Vy and Vz, I have a little volume here in what's called velocity space, whose size is just, dVx, dVy, dVz, right? Just think in calculus terms. Okay? So that is this is just the probability of having the energy, which is a function of velocity, which is just that, times dVx, dVy, dVz. That's all. Very straightforward. Now, where it's not exactly straightforward is that's not a good way to talk about it. Because I don't really want to I don't want to think of Vx and Vy and Vz as kind of varying independently. I really want to have done this in spherical coordinates, where the velocity vector has a length v, and there's a theta, and there's a phi, okay? And I did this before. This becomes p of energy of velocity, and the Cartesian version of that turns into, do you remember, it's v squared times sine theta, d theta, d phi, dv. Because if I have a little increment in theta, that carves out a box, a slice like that, whose length is v d theta. And then if I have a little increment in phi, I have a little side here whose length is v sine theta d phi. And then if I vary the total magnitude of the velocity, I get a final volume which has a dv in it, and that's the whole so-called volume element, right? So that's straightforward. And the probability of v dropping the vector sign between v and v plus dv equals this beast integrated over d theta and d phi. And the integral of sine squared, it's not sine squared, sine theta d theta from 0 to pi, and d phi from 0 to 2 pi. Well, that's 2 pi. Integral of sine theta is cosine theta with a negative sign from 0 to pi is minus, cosine of pi is minus 1, minus cosine of 0 is 1. That's 2, so it's 2 times 2 pi is 4 pi. All right? And so this is just p at e at v, v squared dv, 4 pi. Okay? Which is 4 pi c e to the minus mv squared over kt, the 2 in it, v squared dv. I'm almost done. You may start to recognize this if you've seen the Maxwell-Boltzmann distribution. Let's go ahead and find c. The total probability, 1, is equal to the integral of all of this. 1 is equal to the integral from 0 to infinity of the whole thing, 4 pi c e to the minus m numerator, mv squared kinetic energy kt, v squared dv. Right? That's just, I define that. That's how I'm going to find c. Right? Just got to find the normalization by saying the probability of having any old velocity is total probability is just 1. If you look in the front of the book, this is basically the integral of e to the variable squared times the e to the minus variable squared with a constant out front times variable squared dv. This beast, the integral, turns into 1/4 of pi over a. Where this stuff is a. All right. So I have 1 equals 4 pi c times pi times the square root of pi times 1/4 2kt over m to the 3/2. And if I 4 cancels there, I threw an extra pi in. This pi is that. I rearrange and solve. This is m over 2 pi kt to the 3/2. And finally, we want n of v equals the number of atoms or molecules per unit volume with v between v and v plus dv. Okay? This is all very straightforward. It's just simple definitions. I found c. I plug c in here. That's the probability of an atom having a velocity in the range dv. The number per unit volume is n over v times the probability of v between v and v plus dv. So it is simply combining terms. Okay, that's c. N over v, 2 over root pi. That comes from combining the 4 pi with the term in the denominator there. M over kt to the 3/2. E to the minus mv squared of 2kt v squared. So this is n of v. Sorry. I said something slightly wrong. I seek n of v, which is this density function. I always have to write n of v dv. That's a real number. That was a thing where I had dV on the other side. But then if I write this n of v alone, that's called the density or the probability distribution or the number distribution, okay? Then I drop the dV on either side. Although this is that thing that if I actually want to know how many atoms there are, I better ask within a dV range, and I better multiply it by dV. So this is a very famous result. This is called the Maxwell-Boltzmann distribution. And this is the first big result from statistical mechanics. It's a little bit tedious, but I was just doing, I was just basically just playing with this Boltzmann term. And though, which was not trivial, realizing, this happens a lot. In statistical mechanics, this is the sort of reasoning you've got to do, is sort of figuring out, well, how many, the game is in doing things like going from here to here, and just using this, this Boltzmann term. So that's what I've done. And this is a pretty profound result. I mean, it happens to be right. Yeah?
Why isn't the v squared and the n over v?
Oh, sorry, this is volume. Volume. Okay, in fact, well, okay. Then this, I'm following the notation in the book. Ordinarily, I would have called this little n, and I would have called that f. But OK, fine. This is just the number per unit volume. OK? So I multiply the number per unit volume of atoms. I multiply the total number of atoms divided by the volume of the box. That's the number per unit volume multiplied by the probability. That is the number per unit volume. And this is really profound. I mean, think about the abstract thinking I've done. I said the way I ought to analyze things is in this number of states. I argued from a few applications how this number of states counting works. I gave you some examples. Then I said, I'm going to forget about the details of how it worked. And we made this little derivation where I just drew the big box and the little box. And about the only rabbit I pulled out of a hat was I said, let's take a logarithm before I do a Taylor series. That's all I did. That is all I did. I mean, I went through a very careful sequence of logic, but that's all I did. And I derived this formula. I remember when I think I've said this sort of thing a lot, but it's true. When I was a freshman, I was exposed to this formula with no derivation, and it blew my mind, because it just, it's got an exponential in it, which is kind of weird. You got v squared there, you got, there's a lot of stuff going on here. But we've just derived it. I mean, this is a reasonably rigorous derivation, okay? And it's right. It's right. If you measure, like I said, this is one of the early measurements of gas properties, was people found ways kinetically to measure the velocities of atoms. So they're very high, right? Hundreds of meters a second. Typically several hundred, many hundreds of meters a second. And they've plotted the number that had a given velocity. Out here, this exponential dominates. Down at low velocities, there's the v squared term dominates and takes it to 0 as the velocity goes to 0. And this is n, and this is v. And then we can ask various questions. We can ask, what is the average velocity, right? And that's simple. You would just take v times n of v. And I'm going to assign some homework where you just go through and do that, right? And you calculate. Or I could ask, what's v squared average? And you would do that, okay? What's VRMS? VRMS is just the square root of v average squared. That's what it means, root mean square. Root mean square, okay? And that's a number that is typically about right there. You could ask, what's the peak? That's not so meaningful. VRMS is sort of the most physically meaningful average that you can get out of it. Note that if you ask the average energy, that's just to ask this. That's the average energy of an atom in there. Okay? And this is the formula, which is 3kt over m, which is a famous result you may have seen before. And that's just from explicitly doing this integral, which involves the front of the book integral, which I used over there to find c. Okay? Well, no. Sorry, it's not exactly the same because we'll end up with V fourth, but okay, that's to work out. All right. Let me introduce just one final concept. If I have continuous distributions, here I had a continuous distribution, and actually it's a little unusual compared to the other things we're going to do, because I actually cared about velocity. But if the energy is continuous, once again, I'm going to ask about the probability of E between E and E plus dE. I wish there was some shorthand for writing that out. But it is just the probability of E. But it's not just times dE. We have to put in another little factor there. Remember I said, and the book kind of goes through this, the book talks a lot about this. It's a straightforward idea. It's just that you often have more than one state with the same energy. This is an exact example of it. If I just said the velocity vector amplitude, v, not vector v, just the magnitude v, that would be, I can describe a state that has a v and it has an energy. But if I wanted to talk about the number of states total, the fact that the velocity pointed any one direction had to be taken into account. So I had to go to theta phi, I had to integrate over them. I picked up this factor of 4 pi and the v squared. Otherwise I would have had just a dv. This term is just going to be basically, in this case, we don't really use that language, but 4 pi v squared would have been like this d of e. So really just d of e, dE, is the number of states with energy between E and E plus dE. And d of E itself, and this is an important thing, it comes up a lot. You'll hear this a lot in physics. It's called the density of states. It's not a probability in the sense of it's not a probabilistic idea, but it's just like we've been doing with probabilities. It's a distribution function. It's something where I have to multiply it by dE in order to get a finite number out of it, but it's just sort of giving me, the pair of them is giving me that. And there's nothing else to say about it. And when we pick up next time, we'll calculate a couple of examples of d of E. Okay? The density of states. Have a nice weekend.